Good day, grade 10s. Today we're going to do electric circuits again. This will be the part 2 part. And we will start with resistance. So what is resistance? Resistance is a measure of how hard it is to push electricity through a circuit element, right? Yeah, through a circuit element. And then what causes resistance? On a microscopic level, electrons moving through a conductor. So this is the conductor. So we have a conductor. So this is a conductor. And then we have these electrons. These are electrons, right? So we have a conductor and then we have electrons. The electrons moving through a conductor, they collide or interact with the particles of which the conductor or metal is made. So the conductor is made of obviously different particles. So let's say this conductor is made of different particles. So these are the particles of the conductor, right? So these are the particles of the conductor. So as the electrons move, right, as they are busy moving inside the conductor, they experience collisions. They collide with the particles, right? So when they collide, they transfer kinetic energy. So as they are busy colliding, then they transfer kinetic energy. So the electrons therefore lose kinetic energy and then they slow down, because now they are transferring that kinetic energy and they are colliding. They end up slowing down. As they slow down, this leads to resistance. The transferred energy causes the resistor to heat up. So because they are transferring kinetic energy, that kinetic energy is released in the form of heat, and that measure of heat that is released when the electrons are busy colliding inside the metal or conductor is what we measure as resistance. The transferred energy causes the resistor to heat up. You can feel this directly if you touch a cell phone charger. So if I touch this conductor, for example, or a cell phone charger, I will feel the heat, right? The heat that I feel is because of now the energy that was in the form of kinetic energy has now been converted into heat energy. So the charger gets warm because its circuits have some resistors inside have some resistors in them, right? And then here are the different examples of resistors, as you can see here on this picture. So that's how the whole process happens. Is that as the electrons are moving through the conductor, they collide with the particles of the conductor, and then because they are colliding, they lose kinetic energy, which is now turns into a different form of energy, which is heat, and then you find out that the conductor heats up and then heat is released. So we have a heat released. Yeah, so that's what causes the non-resistance. So resistance slows down the flow of charge in a circuit. The unit of resistance is the ohm. So the unit of resistance is the ohm, which is defined as volt per ampere of current. So the unit of resistance is the ohm. And then fluorescent light bulbs. So we have fluorescent light bulbs. Fluorescent light bulbs do not use thin wires. They use the fact that certain gases glow when current flows through them. They are much more efficient, much less resistant than light bulbs. So fluorescent light bulbs, they take advantage of the fact that current can flow through some gases, So you can have, for example, this light bulb which is fluorescent, right? So what is happening is that as current reaches this point, you have a gas here. So you have a gas here. So you have a gas here, and then this current, when it reaches this point, it heats up here. It can be able to make to actually travel in between. So as the current travels in between here, right, while it's busy heating, creating heat, while it travels through the gas, it causes the fluorescent light bulb to actually light up. So then it lights up. So that's what happens, right? So, and the fluorescent light bulbs, they are much more efficient since they have much less resistance than light bulbs. So they have very less resistance than light bulbs. Than light bulbs. And then the light bulb filament, all conductors have some resistance, right? So all conductors have some resistance. For example, a piece of wire has less resistance than a light bulb, right? But both have what? Both have resistance. A light bulb is a very thin wire surrounded by a glass housing. The high resistance of the small wire filament in a light bulb causes electrons to transfer a lot of their energy, kinetic energy, in the form of heat. That's why when you can touch it, you will feel that there's a lot of heat that you can feel, right? The heat energy is enough to cause the filament to glow white hot, which produces light. The wires connecting the lamp to the cell or battery hardly even get warm while conducting the same amount of current. This is because of their much lower resistance due to their larger cross section. They are thicker. An important effect of a resistor is that it converts electrical energy into other forms of heat energy. Light energy is a byproduct of the heat that is produced, right? So the resistor, an important effect of a resistor is that it converts electrical energy. So we have electrical energy as the input, right? So we have electrical energy as the input, and then if this is a resistor, what happens is that then you have an output that is heat energy, which can also become what? Light energy. And then we see this when, for example, we can have a bulb here, etc. So then we'll have the byproduct as light energy, as the byproduct of heat that is produced, right? There is a special type of conductor called a superconductor. So we also have what we call a superconductor. A superconductor that has no resistance. But the materials that make up all known superconductors only start superconducting at very low temperatures. The highest temperature superconductor is mercury, barium, calcium, copper oxide. So as you can see, it's HgBa2Cu3 oxide, which is superconducting for temperatures of minus 140 degrees Celsius and colder. So it's superconducting at minus 140 degrees Celsius. So what you need to know is that superconductors, they conduct electricity with zero resistance. They conduct electricity with zero resistance, and then they also expel magnetic fields when they are cooled below a critical temperature, and they expel magnetic fields when cooled below some critical temperature. When they are cooled below some critical temperature, they expel magnetic fields. So because of this, electric current is able to flow indefinitely without being lost, right? And then the physical attributes affecting resistance, this is not in caps, meaning this is not part of the syllabus, but it's good for knowledge, right? So the physical attributes affecting resistance, the physical attributes of a resistor affect its total resistance, and those are length. If a resistor is increased in length, its resistance will increase. What does that mean? It means that resistance is directly proportional to length. When length increases, resistance also increases. Typically, if you increase the length of a resistor by a certain factor, you'll increase the resistance by the same factor. So this is the relationship we have. So this relationship just means that resistance is directly proportional to length of conductor. Very important to specify. We should say the length of the conductor. And then the other is also the width or the cross-sectional area. The width or cross-sectional area. If a resistor provides a larger pathway by being made wider or broader, then more current can flow through it. If the total surface area through which current flows or cross-sectional area is increased by a factor, the resistance typically decreases by the same factor. So this means that resistance is inversely proportional to the cross-sectional area. So meaning that, so this relationship here tells us resistance is inversely proportional to cross-sectional area of the conductor. So this means that when the cross-sectional area of the conductor is bigger, the resistance is going to be smaller, and when the cross-sectional area is smaller, the resistance is going to be bigger. So we can visualize this by saying, if you look here, I have a conductor, right? This is my conductor and this is the cross-sectional area, and then I have another small conductor. The area is small, so I have A1 and A2, right? So this one has a small area, cross-sectional area, and this one has a bigger cross-sectional area. So it means that this conductor will have it will have less resistance. So there will be less resistance here, and this one will have it will have a large resistance because of the cross-sectional area is small. It means the electrons or the charges, they will be close to one another, so they will be able to collide, while in this conductor, because it's wider, the electrons will be free to move without affecting each other or colliding most of the times, right? So then now, and also length. So in terms of length, we have length. If the conductor is longer, so here we have a longer length. Then we also have shorter length. So if the length is longer, then the resistance will be higher. And then if the length is shorter, then the resistance will be small. The resistance will be low. Now, this thing of the longer the length, the higher the resistance, I want you to go and find out. You know that power lines of electricity, sometimes they can transport electricity at long distances, right? So you must ask yourself questions. How do engineers at Eskom make sure that the electricity that is transported at long distances from a power station to a town that is maybe in a far place, how do they make sure that the resistance of those wires that transport the electricity, how do they make sure that they don't the resistance is managed in such a way that the electricity is not lost along the way, right? That's a question for you that you can do research on. It's an interesting question. If you want to pursue electrical engineering in the future, you can do research about this and find out the answer by yourself and ask yourself, why is it that there are some power lines that actually transport electricity at far distances, but the electricity is not lost along the way? So what do they do to those power lines? How are they designed? That's a question for you to answer and do research on. Why do batteries go flat? Why do batteries go flat? Battery stores chemical potential energy. So if we have a battery here, right? So this is the battery. So a battery stores chemical potential energy. When it is connected in a circuit, a chemical reaction takes place inside the battery. So once we connect the battery to a circuit, right? Once we connect the battery to a circuit, a chemical reaction takes place inside the battery. So chemical reaction happens inside the battery. A chemical reaction happens inside the battery, which converts chemical potential energy to electrical energy. So this chemical reaction that is happening, and this chemical reaction converts chemical potential energy into electrical energy. Into electrical energy. In the form of electrical energy, this can be made to do what? To do things like heat, or for light bulbs, maybe to do light. So E energy and light energy, right? Yeah. Then since according to the law of conservation of energy, right? We know that according to the law of conservation of energy, energy is always conserved, right? So when all the chemical potential energy inside the battery has been converted to other forms of energy, then a battery goes flat. Then a battery goes flat. So when all the chemical potential energy inside the battery has been converted to other forms of energy, which can be heat or light or others, then the battery goes flat. Yeah. So then the battery goes flat. It goes flat because then there's nothing for it to produce, because it has now used all its chemical potential energy, and that chemical potential energy was converted into electrical energy, and the electrical energy was then used to do heat energy, and also to do light energy and other forms of energy. And then once all that chemical potential energy has been used up, all of it, then the battery will go flat, because it no longer has any chemical potential energy inside it. So then the battery then goes flat, right? Then I want you to do your own research, right? Why do phone batteries go flat, but then they are able to get to be charged, and then they now regain power? Some batteries, when they go flat, they cannot be used again, right? But with phone batteries is different. They can be charged. So they can be charged and then they are used again. So when a phone goes flat, we don't remove the battery, right? We don't remove the battery of the phone, we charge it. So it's your job to go and do a research. Why is it that phone batteries, even when they go flat, we can charge them? So the chemical reactions that happen inside the phone battery, how special are they? How special is the chemical potential energy of a phone battery? That is a question you must answer by yourself, by doing research, if you aspire to be a scientist or an engineer one day. So now, resistors in electrical circuits. So resistors in electrical circuits. It is important to understand what affects adding resistors to a circuit on the total resistance of a circuit and on the current that can flow, right? So we need to understand what happens if I have a wire here. If I add one resistor, if this wire has only one resistor, right? So I have situation 1. And in the second situation, I have 2 resistors. So situation 2. So here we have 1 resistor, and here we have 2 resistors. We need to ask ourselves, how does this affect the flow of electric charge or current, right? And we need to understand that these ones, they are actually, you have series resistors, right? So, and we can also have a situation of what? We can also have a situation like this one, where we have resistors that are not in series, but they are actually in parallel. So how does electric charge flow? How does electrical charge flow in both situations? So here we have parallel resistors. So we are going to now discuss both scenarios for series resistors and parallel resistors. So we're gonna start with resistors in series. So for resistors in series, we have that current. For resistors in series, current is the same. So current is the same at every point. in the circuit. So for resistors in series, current is the same at every point in the circuit, but the voltage is not the same. The voltage is divided. So the voltage is divided across the resistors. The voltage is divided across the resistors, and then this will be in the form of voltage of the battery is equals to voltage V1 plus V2 plus V3, where 1, 2, 3 they represent points on the circuit, right? So they represent points on the circuit. So the resistance to the flow of current, right? The resistance to the flow of current. And now resistance R, right, is directly proportional to voltage V. So meaning we have this situation. It means high voltage can lead to high resistance, right? So then if we pick this formula, V battery equals to V1 plus V2 plus V3, right? We can then have a situation where we have that V1 is directly proportional to R1 and V2 is directly proportional to R2 and V3 is directly proportional to R3. So if we draw a circuit, and also we can say V battery will represent the total resistance. So V battery is directly proportional to basically what we call as R total, right? And then, or we can call it R series, or we can call this its series, right? And then this will be our circuit, right? So if we have a circuit, this will be the circuit, for example, where we have R1, we have R2, and we have R3. And then if we now combine this, if we combine this, and we combine this, and we combine this, and we combine this, on this formula we can just replace. So we can write the formula V battery equals to V1 plus V2 plus V3 for this circuit, right? And why I see V battery, because V battery is directly proportional to R total or R series, then I'll just write R total is equals to V1 is directly proportional to R1, meaning when V1 increases, R1 increases, right? So I'll just replace it with R1. And then V2 is directly proportional to R2, I'll just replace it with R2. And V3 is directly proportional to R3, I'll just replace it with R3. And then R total, because of this is a series circuit, right? So then we can just write R total as Rs equals to R1 plus R2 plus R3. Then this is how we calculate the total resistance of a circuit, of a series circuit. So in a series circuit, this is the formula we will use to calculate the total resistance. So total resistance in a series circuit. And then in a series circuit, we need to know that current is the same everywhere. So it means that if here it's 0.5 amperes, it's going to be 0.5 amperes here. You'll have 0.5 amperes here. You'll also have 0.5 amperes here. You'll also have 0.5 amperes here. And you'll also have 0.5 amperes here, 0.5 amperes. So meaning current is the same at each point. So current is the same at each point on the circuit. At each point in the circuit. Current is the same at each point in the circuit, right? And then now we can look at examples. We have a circuit contains two resistors in series. The resistors have resistance of 5 ohms and 17 ohms. So now we want to calculate the total resistance. So because this is a series circuit, right? So we know the total resistance of a series circuit is Rs. How many resistors do we have here? So we have R1 and R2. So I'm going to say R1 plus R2. And then we have 5 plus 17. And then 5 plus 17 is how much? Is 22. So we have 22 ohms. Then example 2, a circuit contains 3 resistors, which I'll call R1, R2, and R3. The resistors have resistance values of 0.5 ohm, which is R1, 7.5 ohm, and 11 ohms. So R1 is 11 ohms, R2 is 0.5 ohm, and R3 is 7.5. Because this is a series circuit, again, how do we know it's a series circuit? A series circuit is when the resistors are all in the same wire. Can you see that all these resistors, they are all sitting on the same wire? So they are in series. That's what it means to be in series. It means they are all on the same wire. So now we do the total resistance, which is Rs. We're just gonna say R1 plus R2 plus R3, and then R1 is 11 ohm, R2 0.5, R3 is 7.5. And then when we do the calculation, we have 0.5 plus 7.5 is 8. 8 plus 11 is 19. So the total is 19 ohms. Example 3. A circuit contains 2 resistors in series, which we'll call R1 and R2. And the resistors have resistance values of 750 kilo ohm and 1.7 mega ohm. Now R1 is equals to 750 kilo ohm, and kilo means 10 to the power 3. So this is the same as 750 times 10 to the power 3 ohm, which we can write it at 750,000 ohm. And then R2 is equals to 1.7 mega ohm, and we know the mega stands for 10 to the power 6, right? So the mega stands for 10 to the power 6. So mega is 10 to the power 6, so I'm going to write it as 1.7 times 10 to the power 6 ohm, right? And then when we do the calculation, we will get the answer of 1,700,000 ohms. Then now we can, because this is a series circuit, right? This is a series circuit. Then the total resistance Rs is just going to be R1 plus R2. And then we do the calculation, 750,000 plus 1,700,000. Then we are going to get what? So then our answer will be 2,450,000 ohms. This will be the resistance. That's a huge resistance. The diagram shows an electric circuit consisting of a cell and 2 ohmic resistors. This is example 4, right? The potential difference across the cell is 13.5, which is V total, right? So this is 13.5 here. And the potential difference across resistor 1, V1. So if I use a voltmeter to measure it, so this will be my V1, right? And then the V1 is measured to be what? 9.4 volts. And then now we want to know what is the potential difference across R2. So we want to know V2. So we want to know what V2 is, and this is what? This is a series circuit. And in a series circuit, we know that a voltage or potential difference is divided, right? Is divided. So it means if it's divided, it means V total is actually V1 plus V2. That's what being divided means, right? And then so it means it's split, it's sort of shared between the resistors, right? So the V total from the battery is what? The battery supplies 13.5 volts. And then what is V1? What is V1? And then V1 we know is 9.4. We are given 9.4 volts. We want to know V2, right? And then to find V2, we just take 9.4 to the other side, and then we have 13.5. When a number jumps the equal sign, it becomes a negative, so we have minus 9.4 equals to V2. And then 13.5 minus 9.4 is how much? 13.5 minus 9.4. 13.5 minus 9.4 gives us 4.1. Therefore, it means V2 is equals to 4.1 volts. So V2 is equals to 4.1 volts. So this is 4.1 volts. Let me write it well so that it doesn't look like an R. So then V1 is just, V2 is just 4.1 volts. And then now we are going to talk about the resistors in parallel. Resistors in parallel. So when resistors are in parallel, right? Current is divided. Current is divided when resistors are in what? When they are in parallel. Current is divided. So let's look at our parallel combination. So I'm going to draw a parallel combination. Let me use a black marker. So this is I have a circuit here. So I have this circuit, and then we have a resistor, and then we have a resistor here, and we have another resistor here. And then I'm gonna color these resistors with blue just to decorate them. So those are my resistors, and I'll call this one R1 and this one R2, and then this one I'll call it R3, right? And then after that, so we say current is what? Current is divided, right? So the current that is coming here, so if I have a current that is moving towards this parallel combination, right? So this current, I will call it current I, right? Which is basically I total. It's representing I total. When this current gets to this junction, it's going to be divided. The other part of the current is going to move in this direction, and the other current will move that direction, and the other current will move this direction. And then I'll call this one to be I1, and then the one that moves towards R2, I will call it I2, and the one that moves towards R3, I'll call it I3. Now, what is happening here? What is happening is that the total current was divided into three currents, which is I1 plus I2 plus I3. So this happens in a parallel circuit. So when a circuit is parallel, the current is going to be divided at the junction, and it will be shared among the resistors that are in parallel. So here, since the three resistors are in parallel, then they will share the total current together, as you can see here, right? But now let's talk about the potential difference The potential difference of a parallel combination is not divided, is the same. Why is it the same? It is because when we measure the potential difference, we are measuring it at this junction here. So if I draw the same circuit now, so I'm gonna say a voltage is the same for parallel. We need to specify that parallel combination, not in a parallel circuit, no, for parallel combination, because a circuit can be a series circuit and be a parallel circuit at the same time, have sections that are parallel and sections that are in series. So you need to specify that voltage is the same for what? For parallel combination. And then when I do the same thing, we'll draw the circuit here. This is our parallel combination. This is our parallel combination. And then we have our resistors. R1, resistor R2, resistor R3, right? So when we measure the voltage here, we will measure it from there, from that junction. So using a voltmeter, when we measure the resistance, we'll measure it from there, right? So the resistors that we measure, the voltage that we measure here is the voltage of this whole combination, right? So if this resistor, this voltage, it's 15 volts, it means the voltage of this resistor is gonna be 15 volts, and the voltage of this resistor is gonna be 15 volts, and the voltage of this resistor is also gonna be 15 volts. So that's what we mean, that in a parallel combination, all the resistors in a parallel combination, they all have the same what? The same voltage. That's very important. They all have the same voltage. But we need to specify what we are saying when we say the 15 volt is, we are referring to basically the whole wire from this junction to this junction is actually having a voltage of 15 volts, right? Yeah. So this wire has 15 volts. This wire from this junction to this junction is measured as 15 volts, and then this wire from this junction to this junction is also measured at 15 volts. That's what we are saying, right? And then now we have to find a way to determine the total resistance in a what? In a parallel combination. So now we're gonna use this fact. We are going to use this. So we know that so I'm gonna write it here. So we know that I'm gonna just border this here. So we know that current is inversely proportional to resistance, meaning when resistance increases, the flow of charge is going to be slow. You know that, right? We have discussed that when resistance increases, current decreases, and vice versa. So it means that we have a situation where we have I total is gonna be inversely proportional to what? To R total. But this one is for what? Is for parallel P, right? And then we have I1 is going to be inversely proportional to R1, and I2 is inversely proportional to R2, and I3 is inversely proportional to R3. So now when we combine this, and this and this and this, and then we replace them here. What do we get? Then where I see I total, I'm going to put 1 over R total, or 1 over RP. So then I'm going to have this situation. So then I'll have 1 over RP is equals to, where I see I1, I'm going to replace it with 1 over R1, plus where I see I2, I'm going to replace it with 1 over R2, and where I see I3, I'm going to replace it with 1 over R3. And then this is the formula that we use to calculate the total resistance in a parallel combination. Total resistance. So do you see where the formula comes from? So this is how the formula is actually derived. Yeah. So then now, when we want to determine the total resistance in a parallel combination, we're going to use this formula. And then now we can now get into examples. So we have the first example. Consider the following circuit. What is the voltage across the resistor in the circuit shown, right? So because we only have one resistor, so we have one resistor, right? So it means the voltage that we are going to measure here is going to be 2 volts, because we only have one resistor, right? So V1 is basically 2 volts. Since there is no other resistor, that voltage is going to be used by only one resistor. And then now we have example 2. Consider this circuit. What is the voltage across the unknown resistor in the circuit? The unknown resistor in the circuit. And then now we have what? We have a series. This is a series circuit, as you can see, right? This is a series circuit. So what do we have here? In a series circuit, voltage is what? Voltage is divided or shared among resistors. So what is going to happen here? It means this one here represents the total resistance, the total voltage. So this represents V total, which I'll write as V total is equals to what? Is divided or shared among VA and VB. And V total is 2 volts, and VA is what we are looking for, and VB is 1 volts. And then we take 1 to the other side, we'll have 2 minus 1 is equals to VA, and then 2 minus 1 is 1. So therefore VA is just 1 volt. So we're going to have 1 volt here. And this makes sense. 1 volt plus 1 volt is 2 volts, because the 2 volts was shared among the 2 resistors. Then example 3. Now we have a circuit where we have 3 resistors, right? And then this is the total. We have 3 resistors, and now this is the total voltage. This total voltage is shared among 3 resistors. So the 7 volt total voltage is shared among 3 resistors. It is shared among 3 resistors, and we know that this is a what? This is a series circuit, because the voltage is shared, and that's why the voltage is shared, right? So then we have V total is equals to VA plus VB plus VC, and V total is 7, VC is 4, 1 plus 4, we get 5 plus VB. We take 5 to the other side, we have 7 minus 5 is VB, 7 minus 5 is 2, and then VB is 2. Therefore it means VB is 2 volts. So it means the volts here just 2 volts. Example 4. Consider the circuit diagram. what is the voltage across the parallel resistor combination in the circuit shown? Hint, the rest of the circuit is the same as the previous problem. So what is the voltage across the parallel resistor? So now to find the voltage across the parallel resistor, the voltage across the parallel resistor. So we see that here we have 4, right? And this is the total. This is V total. But what did we say? We said that for resistors that are in parallel, they all have the same voltage because their voltage is going to be measured in this junction. So the voltage that is measured in this junction is actually the voltage of all these 3 resistors. So it means whatever that we measure here represents the voltage of each resistor basically when they are measured. So it means because we have 4 volts here, the voltage that we will measure here. So we want to know this voltage. What is this voltage here? And this voltage that is here, let me call it voltage A, right? So then V total will have V total is equals to 4 plus 1 plus VA, right? And then VA 4, we know V total is 7, and then 4 plus 1 is 5, and then we have VA. So 7 minus 5 is equals to VA, so 2 is equals to VA, so VA is 2 volts. So it means the voltage measured from this junction is actually how many volts? It's actually 2 volts. So what does this tell us? It tells us that the voltage for this parallel combination is actually what? It's actually 2 volts. So the voltage across the parallel combination is 2 volts. And also what we can do is that we can turn the whole parallel combination and treat it as a single resistor. So meaning we can turn this circuit to be in this form where we still have the resistor 1 volts, and then we have this resistor here which has 4 volts, and then we have this resistor here which has what? 2 volts, and then this resistor here, this represents the parallel combination. That represents the parallel combination. And then example 5, the following circuit diagram shows 2 resistors connected in parallel with each other and with the battery. Resistor 1 has a resistance of 3 ohms. Let's write it down. So resistor 1 has a resistor of 3 ohms. And then resistor 2 has a resistance of 6 ohms. The total current is 18 amperes. Find the current through resistor 1 and resistor 2. So we are going to find the current through resistor 1 and resistor what? And resistor 2. So this is then what we are going to do. We can see that the total current comes from what? The total current comes from the battery. So this represents the total current. So this arrow represents the total current, I total, which is equals to 18 amperes. When this current reaches this junction, it's going to be divided. The other current is going to move this direction, and the other current is going to move this direction. So we're going to have I1 here, and we're going to have I2 here. And then from this, we can generate the first equation. So we're going to have I total is equals to I1 plus I2. But I total is 18, so 18 is equals to I1 plus I2. So then we'll call this equation 1. And then I'll just we have the first equation. And then after that, we know that resistance is inversely proportional to current, right? So it means we can say I1 is inversely proportional to R1, right? And I2 is inversely proportional to R2. Now, when we divide these two, so when we divide them, so I'll call this to be I'll call them equation A and equation B. So when we divide them, equation A divided by equation B, we're gonna have I1 over I2 is equals to 1 over R1 over 1 over R2. And then when we do it, then we'll have 1 over R1 divided by 1 over R2, and then we have I1 over I2 is equals to 1 over R1. When we change the division into multiplication, then we'll have R2 over R1, and then I1 over I2 is equals to R2 over R1. And then now we can put in the values. I1 over I2 is equals to R2. The value of R2 is 6 and the value of R1 is 3. And then we have I1 over I2 is equals to 6 divided by 3 is 2, right? And then now we can come here and say, therefore, I1, when we now do cross multiply, we'll say over 1 and do cross multiply. And then we'll have I1 is equals to 2I2. And then we will call this equation 2. And then we can just circle it. This is our equation 2, right? Then after that, we can now solve them simultaneously. So then I'm going to say substitute equation 2 into 1. So where I see I1, I'm going to put 2I2. So then we have 18 is equals to 2I2 plus I2. And then we have 18 is equals to 2I2 plus I2 is 3I2. And then we divide both sides by 3. And then 18 divided by 3 is 6. Therefore, I2 is 6 amperes. So it means I2 is 6 amperes, right? And then now we're going to say substitute I2 into equation 2. And then where we see I2, we put 6. So I1 is equals to 2I2. And then 2 times 6. And then we get 12 amperes. And then this is I1. So then our answers are I2 is 6 amperes and I1 is 12 amperes. So it means we have I1 is 12 amperes and I2 is what? I2 is 6 amperes. And 12 amperes plus 6 amperes gives us what? It gives us 18 amperes. And then in contrast to the series circuit, when we add resistors in parallel, we create more paths along which the current can flow. By doing this, we decrease the total resistance of the circuit. So take a look at the diagram below. On the left, we have the same circuit as in the previous section with a battery and resistor. The ammeter shows a current of 1 amperes, right? And then adding a resistor to the circuit in parallel decreases the total resistance, as you can see. So components connected in parallel always have the same voltage. Right? So if the bulbs are connected in parallel, so we'll say that the bulbs have both the same resistance and same potential difference. So this is enough to make the power of bulbs the same. And if we add another bulb in parallel, for example, right? So if we add another bulb in parallel, if we add another bulb in parallel, the bulb will have the same voltage as the other bulbs. So the bulbs will be bright as before. Then now here we have an example where we have a circuit that contains two resistors in parallel. The resistors have resistance value of 15 and 7 ohms. So I'll call this resistor 1 and I'll call this resistor 2. So we want to determine the total resistance. So since this is a parallel combination, right? So we're going to use 1 over Rp is equals to 1 over R1 plus 1 over R2. So 1 over Rp is equals to 1 over R1 plus 1 over R2. So where we see R1 we put 15, where we see R2 7, right? And then we're going to say 1 over 15 plus 1 over 7 gives us 22 over 105. And then when we flip that, so we know 1 over Rp is 22 over 105, right? So then when we flip that, we will have Rp is equals to 105 over 22. So Rp is equals to what? 105 divided by 22. 105 divided by 22 is 4.77. Then this is the total resistance in the circuit, in this circuit. This is amazing. If these resistors were in series, the total resistance was going to be what? 15 plus 7, which gives you what? 15 plus 7 is going to be 22. So it will be 22, meaning it will consume a lot of electricity, right? But because of now the resistance is 4.77, it's not going to consume a lot of electricity. It's going to allow more flow of current in the circuit. That's amazing. It's amazing. Do you see the importance of parallel connection? And then example 2, we have 3 resistors that are in parallel. So we add a third resistor to the configuration set up in the previous example. The additional resistor has a resistance of 3 ohms. What is the total resistance in the circuit? So now we have R1, we have R2, and then we have R3, right? And then it's going to be the same because this is a parallel combination. We're going to have 1 over Rp is equals to 1 over R1 plus 1 over R2 plus 1 over R3. So when you do that, we have 1 over Rp is equals to R1 is 15, so we have 1 over 15 plus R2 is 3, so we have 1 over 3 plus R3 is 7, we have 1 over 7. So 1 over Rp is equals to, and then we do 1 over 15 plus 1 over 3 plus 1 over 7, and we get 19 over 35. And then when we flip the Rp and we make it the numerator, we get 35 over 19. So Rp is equals to, and then when you say 35 divided by 19, we get 1.84 ohms. What do you see? What do you notice? The more we add resistors in parallel, the lesser the total resistance. So when we add resistors in parallel, we are actually decreasing the total resistance of the circuit. Can you see that? Isn't that amazing? And then we have an exam type question here. So we have 2 identical bulbs X and Y and a measuring device Z are connected to a battery as shown in the circuit below. And the first question says, so this is a switch, right? So this is a switch. And then we have a cell. Which physical quantity will device Z measure when switch S is closed? So when switch S is closed, it's going to measure what? It is going to measure voltage. So it's going to measure voltage because it's a voltmeter. It's a voltmeter. It measures voltage. And the second question says, why will the brightness of the bulbs be the same when switch S is closed? The reason why the brightness of the bulbs is the same is because of the bulbs are in parallel, right? So because of the bulbs are in parallel, they have what? They have the same. So the bulbs are in parallel, so they have the same voltage. So remember we said that in a parallel combination, all the components in a parallel combination have the same voltage, right? So they both have the same voltage. So that will be the answer. And then the third question says, a third identical bulb is connected in parallel with bulb X and Y. Will the brightness of the bulbs increase, decrease, or remain the same? So we connect another bulb here, which we'll call bulb W. So the question is, will the brightness of the bulbs increase, decrease, or remain the same? Now, look at this, right? Bulbs X, W, Y are all in parallel. So they have same voltage. because they have the same voltage, the brightness would be the same. So the brightness will just remain the same. So the brightness will remain the same because the voltage is not going to increase. If the voltage that is measured here is 15 volts and 15 volts, if we include this bulb W, it's also going to be 15 volts. If we include another bulb and connect it here, we call it bulb what? Bulb P maybe. We're still going to have the same thing. We're still gonna have 15 volts. It won't affect the brightness. Very important to notice, right? So the answer here will be what? The answer will be, it will remain the same. The reason why it remains the same, the reason is that parallel bulbs have the same voltage. And then because they are identical, and since they are identical, they have the same power. Because they are identical, so they just have the same power since they are identical. So this is how we, and it means that the current that is moving through each is the same because they are identical. So that is the reason. So this is where our lesson is gonna end. So bye for now. See you next time when we do the kinetic molecular theory.